Testing, 1, 2, 3. Okay, seems like my audio is working. Hello everyone, it is me again, welcome back. For those of you who have been watching since the very beginning, you would know that we have taken approximately maybe a 3 to 4 month hiatus, but now we are back. Chances are, if you're watching this in the future, you will probably be a student of mine, in which case, then these videos will work the exact same as all the previous few that we've seen so far, from quadratic functions and completing a square, all the way to coordinate geometry of circles, and beyond. In other words, what I'm trying to say is, you should have my worksheet with you, first of all, and then you can follow along as we recap the content and try out some of the problems within the same worksheet. Now, one thing I do have to note is that our topic today is Trigo functions, graphs, and equations, which means that we will have a highly computational ordeal ahead of us. And as a result, we will be spending the bulk of our time today on examples rather than pure content. I will also expect you to already be aware of your e-math Trigo stuff for the most part, which means that I will not be spending too much time going over the absolute fundamentals of your Trigo functions. So for example, if I tell you tuakaso, you should know what I am talking about. So without further ado, let's begin. First of all, I want to just say this first page of content over here purely is your e-math content, so I don't really have a lot to say over here. I want to draw particular attention to the conversion between radians and degrees as a measure of angles, because we will be using both in A-math quite frequently. In particular, I want you to be careful of radians. For radians, as long as I don't see the degree symbol, right? In other words, the small little O shape that you see on the top right of a number, as long as you don't see this degree symbol, you can take for granted that the angle is going to be in radians. Take for example, if I have the statement sine 4, full stop. In this case, we don't have the little degree symbol on top, and so we have necessarily to assume that the 4 is referring to an angle in radians, and then you can go on and fool around with what that actually means. So for example, in this case, if we expect 4 radians, then of course you can just divide by 180 degrees and divide by, I clicked something weird, what the heck is this? So in this case, if you want to convert it, you can simply divide by what we know to be 180 degrees, in other words pi radians, and afterwards multiply by 180, and that will get you your degree form. And of course, if you want to convert degrees to radians, just do the opposite. I believe this is quite familiar to all of you who are in my class. Aside from that, we also need to briefly mention the reciprocal Trigo functions. When I take a number, typically 1, and I divide it by a Trigo, we can write it with the shape, or rather with the letters cosecant, secant, and cotangent. We will not use the powers like negative indices, because the negative one index is already used for the inverse Trigo functions over here. And you should already know this from your scientific calculator, of course. Alright? Now, one thing that we like to talk about in E-math is this concept of special angles. So for these specific values, right, 0 to 90 with intervals of 30 degrees and 45 degrees specifically as well, These numbers, when thrown into Trigo, tends to give you special angles. In other words, you will get very special results when you put in these numbers. So how do we read this table? For example, we can expect the sine of 45 degrees to give us root 2 over 2, this value over here. Chances are, when you're in the exam, you might not be willing nor able to memorize these values perfectly. So one little strategy that I have devised up for you is over here. You can simply input these angles into your calculator and then afterwards square the result. So what we can do is you can just type in whatever special angle you have, you get some decimals, you square the result and it will give you a fraction. And so we will undo the squaring by slapping a square root over that fraction, in this case over 3 over 4. And then we will simplify accordingly. By the way, there's a typo over here, in case you didn't notice. The cosine of 5 pi over 4 gives you negative 0.7. We square this to get 1 over 2. And so cosine 5 pi over 4 should be negative square root of 1 over 2. Because there was a negative at the start. You have to preserve that negative, right? And so we'll get negative root 2 over 2. But this is a complicated example, of course. This next portion is an e-math trick as well. If you have 90 minus an angle, you can actually simplify it accordingly. Cosine turns to sine turns to cosine, cosine turns to sine, tangent turns to cotangent. In doing so, you can change 90 minus angle into just the angle by itself. That's perfectly fine. Now, the next thing we're going to cover is something known as general angles. And I believe if you are a student of mine watching this for recap, then hopefully you should be very, very, very familiar with this. To briefly recap, whenever you have angles that are greater than 90 degrees or less than 0 degrees, in other words, negative angles, what we can expect is that the angles will essentially start off from some position on the right hand side and then rotate in an anti-clockwise fashion. So you have all these pictures here as an example. Whenever you have these kinds of rotations, we need to bring up the concept of something known as the basic angle. So what we mean by basic angle is that the basic angle is essentially going to be a specific angle that will allow you to find the value of any Trigo function when you put into the calculator. And how we find this basic angle is to actually specifically look at the distance of, or rather the separation of the original angle, right, the big or small angle, compared to the x-axis, right? So what we mean essentially, I don't know if the text highlighter works. So what we mean essentially is this portion over here. If you have any angle, you can find the basic angle by measuring out the smallest positive angle formed by the line and the x-axis. So if you look at all these diagrams over here, for example, you can very quickly notice that the basic angle is always going to be 30 degrees. In the first example here, between the x-axis and the line is obviously just this angle here, which is clearly 30 degrees. In the second example, we see instead you're going this way, which will be 30 degrees over here because it's 150 on the left, right? Adjacent angles on a straight line. For the third example, what we see is that this line over here gives 180 degrees. So necessarily this small little portion as we go down must be 30. And for the last example, going down here gives us 30 because angles at a point give a sum of 360. This should be somewhat straightforward. right? So we notice that all of these basic angles are indeed 30 degrees. Again, 30 degrees because the basic angle is the separation between the line and the x-axis, not necessarily the positive x-axis, such as in this case over here, right? And over here we have the same scenario. This will be 30, that will be 30, this will be 30, and that will be 30, right? So this is how we will obtain our basic angle from any rotation. It doesn't necessarily have to be nice, right? Such as these 4 examples, they're quite nasty. So whenever you have any scenario, it's always most important to ask yourself, okay, if I have to find the basic angle, how do I compare it to the x-axis, to an arbitrary horizontal? So for example, in this case here, we can expect to measure out a basic angle like this on the first laser, right? Let me increase the thickness. Can I do that? I can do that. And for the second laser, it's actually an obtuse angle, right? You're actually going to get this situation over here. But the basic angle is the separation between the line and the x-axis, or in this case, the horizontal ruler. So we'll actually be focusing here instead. Basic angle. And of course, we can also expect the same of these angles. For these angles, they're a little more special, right? Because this time round, for the lasers that are below, if we imagine this to be the x-axis, you can quite clearly see that because we're starting from the right hand side and going counterclockwise, they're going to be reflex angles. But it's okay. The same method of looking for the separation between the line and the x-axis, in this case, and the ruler, will still work. So for our laser over here, we will simply say that this portion gives us the basic angle. Not this. This is rainbow. That's not the basic angle. And for our last little laser over here, we can expect this small little acute angle here to be the basic angle. Alright? And if we're working with more complicated rotational examples, let's say we have something like that, where our line, or rather the line created by the angle, is no longer as cooperative, right? Looking at the amulets, you'll notice it actually turns outwards, and then it goes even further until this point, right? So what happens if we're doing something like this? In this instance, then what we're going to do is we will simply perform the same check, right? I'm going to draw in my little x-axis, in this case the ruler, right? Not drawn to scale. And from here, all we will need to do is to actually find the separation, and we will do so by asking ourselves, okay, the angle reaches until this position, so how will the line created be? The line created will start from the origin and then afterwards go up to that little point. There afterwards, we just need to find the separation between this line and the x-axis, or in this case, and the ruler, right? So the line and the ruler will form this angle over here. We'll call this the basic angle, right? And once again, same thing over on the other side. So let's say we instead, give me a moment to pen this thing. So let's say instead of having it go anti-clockwise, because that has been all our examples so far with these pictures, what if we weren't so lucky, right? Perhaps you unfortunately are now working in a situation where you go clockwise. So if you recall, for clockwise scenarios, necessarily that will mean that we're going to have negative angles, right? Such as in these two instances over here. So when you have negative angles, fortunately, finding the basic angle will work much in the same way. I simply need to draw the line created by the angle, compare it to the x-axis, and then we will be able to find the separation between the x-axis and that line created. Not necessarily the positive x-axis. Let me say that again. It should be quite clear in this example that you don't actually have to use the positive x-axis at all. That doesn't necessarily have to happen. Right? So, having said that, let's return over here. What I'm going to do next is, let me get this back on, and then afterwards I need to figure out how to use this thing now that, what the heck is this? Now that it updated itself. Fit to screen, oh, that would be very bad for me. Okay, so looking at our third example on the far right, let's say we want to work with something that is a lot more brutal. This time round, I'm actually going to go clockwise like this. So in a situation like that, we can expect the line created to be pointing downwards like that. And when we want to measure the basic angle, we will simply compare it once again to the x-axis, not necessarily the positive x-axis. In fact, in this case, we will indeed have to use the negative side, right? So you'll be specifically looking at this portion over here. That will be your basic angle. All right. Of course, now the next question then becomes, what if I don't have a picture, right? What if we're not actually doing something that is geometric in nature? Maybe we're just working with calculations. So fortunately for you, you can actually use these following conversions that are over here. So if you are in this first little segment over here, we call these four little segments quadrants, right? If you're in this first little segment, that is to say, you started from the right hand side, as we said earlier, and you go by an acute angle, then obviously you are already an acute angle, and so your basic angle will simply be the angle itself. On the other hand, when you are given the basic angle and you want to jump to these other regions, the second, third, and fourth quadrant, right, then you'll have no choice but to follow the formulas that you see on the bottom right. If instead you are starting with an angle and you want to go back to the basic angle, then you'll have to do the exact opposite. So as an example, let's say we have 320 degrees, right? 320 degrees, we recognize it to be something like that. And so the basic angle will be this portion, which is 40 degrees. And how do we get this 40 degrees if we wanted to calculate it? We know that 360 degrees minus the basic angle alpha will give you 320. How do we know this? We get it from this formulation over here. Of course, if your question instead is why do these formulas work, then all I can say is ask me that in class. That is something that I have gone through before, and I don't want to waste too much time on all the derivations in a so-called crash course video. So from here, I think it's quite clear that you'll be able to calculate basic angle equals to 40 degrees very readily. Right? As a more complicated example, perhaps you could ask yourself, okay, what if we have a really large angle? Let's say for example, we are given 420 degrees. What will we do in this case? So first of all, we will recognize that 420 degrees would certainly be an overshoot, right? What I've drawn right now is one round. This is 360 degrees, but 420 degrees is quite a lot larger than that, like this. So perhaps, let's say we're given an angle equals to 420 degrees, then we would say, first of all, let's undo the excess rotation, right? It's not going to be 80. It's going to be 60. So our first step is to undo the excess rotation, which is this portion, and then we'll only focus on this guy. Second of all, then we will go back to our usual strategies. Is it already in the first quadrant? If it's already an acute angle, then you're done, right? This guy is already alpha. But if you're in a scenario where perhaps you're not so lucky, then you might need to do extra work. So let's say we have an angle of, that's not 90 degrees, I wrote the wrong thing. Let's say we have an angle that is a lot more troublesome, 910, what will we do over here? So we will need to first start by getting rid of all the excess rotations. Always remember a complete rotation is 360 degrees. And once we do that, then you'll need to ask yourself, okay, what quadrant is this guy in? In this case, it will be the third quadrant because he is in between 180 degrees and 270 degrees. In other words, he'll be in this region over here. So because he's in the third quadrant, we'll then use this formula here and say that 180 degrees plus the basic angle gives us 190 degrees, from which the basic angle is quite trivial to calculate. Right? And as a final example, let's say we are given the worst case scenario, right? What if it's a big angle except it's in the wrong way? It's going clockwise. So you actually have a gigantic angle and then screw you, it turns out to be negative. What would we do there? So as an example, let's say we have maybe what would be a good example? Let's say perhaps we have negative 5530, like so. So what we will do is, once again, our first step is to undo all of the rotations we don't want. This time around, because the original angle is going clockwise, you'll undo it with a plus 360, not a minus. And in this case, we're going to need to go 15 rounds. So we'll have negative 5530 plus 360 times 15, and when you throw this into your calculator or whatever the heck, you can expect negative 130 as the result. So whoops, it turns out that it is still negative after all, right? It's going to be something like that. Of course, if you are astute, you can very quickly realize if it's negative 130, then quite clearly this portion here, we expect it to be 50, because adjacent angles on a straight line should form a total of 180, and this guy will tell you the basic angle. Otherwise, what you can do is you can actually deliberately go an extra round, and this will give you this guy over here, right? And once you go this extra round, then you can simply go on to ask yourself, okay, how do I find the basic angle? And we will do so by using this formula, right? Now, at this point, if you are lost or if you have no idea what I'm talking about, then I need you to really read this up on your own, because these are the so-called basic fundamentals. I wasn't actually expecting to spend so much time over here, so if you're watching from scratch, you shouldn't be doing that. You should be using the timestamps after the fact, and instead jump to the relevant section. But hopefully you are not completely bored by how easy this section is. So looking at a few example applications, let's say we have a basic angle of 35 degrees. We want to find a possible value if the angle is positive and in the fourth quadrant. So what we will do is we will just recall the fourth quadrant formula. 360 degrees minus basic angle equals to an angle in the fourth quadrant, right? So if your basic angle is 35, then one simple example that you could use would be 325 degrees. In part B, they tell us to find an angle that is negative and obtuse. So this is a little more annoying. You can imagine for yourself, right? These are your four quadrants. If I'm negative, I'm starting this way, and if I'm obtuse, I'm going to be between 180 and 90 degrees. And so we expect to be over here, the third quadrant. Because it's the third quadrant, we will now use a different formula. We'll be using 180 degrees plus alpha. And of course, in this case, alpha is 35. So quite clearly, you can work out 215 degrees. Right? So just a very simple question about conversion. Now that we're okay with this, let me go back up again, because now we're going to figure out what exactly makes the difference between the quadrants. So what if my angle is in the first quadrant, second quadrant? So what if it's big? So what if it's small? So the thing is, depending on what quadrant you're in, it will actually change the plus minus sign in front of the final answer of your trigo. Right? When you are in the first quadrant, everything gives you a positive value. Right? So everything gives a positive result. And if you can take a look at these little letters over here, they will tell you who is the only person who enjoys positive final answers when you're in that quadrant. For example, if you're in the fourth quadrant, you expect to have positive answers only for cosine, right? So for example, the cosine of 300 degrees will actually give you positive half, but the sine of 300 degrees will give you, what will it give you? So let's try using our trick from earlier. If I type sine 300 into my calculator, I'll get negative 0.866. What I'm going to do is I'm going to square this result, and it will give me 3 over 4. I'm going to undo the square by doing a square root, so we'll get root 3 over 2. And because we removed the negative, you need to add back a negative, and you'll get negative root 3 over 2. Right? And therefore, indeed, we see that the sine has given us a negative result, which makes sense. We're in the fourth quadrant. 300 degrees is in the fourth quadrant. So if you're in the fourth quadrant, the only person who enjoys positive answers is cosine. And the sine function, too bad for him, will have to contend with having negative values. Right? So how do we memorize these silly little letters? There's a few ways to go about it. So I guess some schools will teach add sugar to coffee, ASTC, right? ASTC, add sugar to coffee, right? But I personally prefer the extremely memorable and unusual after sex throw condom, ASTC. So hopefully the sheer oddity that is this mnemonic will allow you to better memorize these 4 little letters. Now going back to our practice problems, our last little question over here is pretty interesting. We want a positive sign. We want the angle being negative. So what you can imagine is, if you want a positive sign, the only regions that are appropriate for you will actually be this guy and that guy. But you want a negative angle, and so you might have to do something like that. So once you have this down, drawing in our line, you realize that it's not a line, but you get the idea. You realize the basic angle will be this portion, which is 35 degrees. Necessarily, this means that portion must be 145 degrees, and so this little portion over here must be, let's see, 180 plus 35 must be negative 215 degrees. Of course, the smartest answer is to just choose negative 35. That would be completely acceptable. That would be genius, in fact. Now, let's look at question 6 over here. It tells us that the positive reflex angle A exists such that tangent A is 1 over square root 3. State the value of A in degrees. So, of course, if you want to play cheat and use your calculator, you can do that. But otherwise, you would surely recognize this as a special angle. You should know, hopefully, that A is actually 30 degrees. Thereafterwards, it asks us, can you find the exact value of cosine 120 degrees? So what we're going to do is 120 degrees is in the second quadrant. In other words, the basic angle is actually 60 degrees. And so, the cosine of 120 degrees is essentially the cosine of 60 degrees. That's the whole point of the basic angle, right? You use it to find the value of any weird-ass angle you want. Only problem is, what quadrant is 120 in? 120 is in the second quadrant, isn't it? And that will mean that cosine gives you a negative answer. From here, we know cosine 60 gives us half, and so negative half should be the final answer. Next question asks to find the exact value of cosine 45. That is simply going to be a basic angle, so I will skip that problem. Next problem asks, it is given that sine B is less than 0, and B is between 0 and 360. So we know that sine giving a negative answer means that you're in the third or fourth quadrant, and B is between 0 and 360, which means that we can either have this or we can have that. In both cases, B is going to be reflex, and specifically going to be between 180 and 360 degrees. So that's what we can say about the angle B. The next question then asks, the angle C exists such that cosine C is less than 0. Once again, let's look at our after sex throw condom, and you will see that C, capital C, can indeed never be acute, because the positive areas are A and C, and we are negative right now. So these two places are gone. You're left with the second and third quadrants, and in both of these quadrants, no matter which direction you approach from, you're going to end up with either an obtuse or reflex angle. So you can simply explain that capital C will never be in the first or fourth quadrants, and so he can never be acute. And we are done. Right, so if we're okay up to this portion, I will take a break over here and we will resume in a few minutes. Of course, if you're watching this after the fact, then the wise thing to do would simply be to skip ahead to when we resume. Right, so I will see you in a few minutes and you will see me hopefully instantly. Alright, we are back, ladies and gentlemen. Let us move on to the second portion of today's video. We're going to be looking at the graphs of Trigo functions. So, what we need as far as A math goes is we need to know how to draw the graphs of sine, cosine, and tangent. Now, the general shape of your sine and cosine graphs is particularly important because they will always look like a wave like this, and there are a few important words that I need you to know, right? So let me zoom out a little. So the first thing we need to know is, especially for those of you who are not physics students, is that for any wave-shaped graph, right, let's try something like this as well. For any wave-shaped graph, there is a certain word that we use called amplitude that describes, informally, right, because we're not in physics class here, informally it describes the distance between a maximum minimum point from the center of the waveform, right? And what do we mean when we say center of the waveform? This horizontal center, right? This horizontal center is known as the axis of the waveform, of the sine curve. And therefore we say that the amplitude will be the maximum vertical distance of the graph from the axis. In other words, if this is the axis and then I have this wave here, the maximum distance between the axis, the dotted line, and the graph necessarily has to be the vertical distance between the axis and either the maximum or the minimum point. Last but not least, we also introduced the idea of the period of a curve. Now, unlike in physics where period describes the time interval required for one complete oscillation of some periodic motion, in math, because we don't necessarily measure with time, it is simply the amount of resources required in order to travel one full cycle. In this example over here, we know that this is one full cycle. It is the repeating unit, to borrow a word from your O-level organic chemistry, right? So the repeating unit has a length of 360 degrees, and therefore it means that I need to travel 360 degrees if I want to create one complete cycle. In other words, 360 degrees is the amount of resources consumed in order to create one complete cycle. So math is a little more general, right? Physics tells you the time consumed for one cycle. In math, it is the amount of whatever resource consumed for one cycle. So the resource could be degrees, it could be radians, it could be time, it could be just about anything. It depends on the independent variable, alternatively the x-axis. Right? Cosine is a little different from sine, which is what we saw earlier, in the sense that if you compare the two, cosine actually starts from a maximum, whereas with sine, you are starting from the origin, 0, 0. So over here we have the brief differences between sine and cosine, and we can demonstrate this by actually attempting to draw them both. Let's use radians just for the heck of it. So for sine, once again, please recall, we will actually start off on the origin, and then we will go up and go down. One complete cycle should be 360 degrees, alternatively 2 pi. The middle will be the middle, and therefore it's pi. And the first peak is the middle of the middle, in other words pi over 2. And the first trough, alternatively the first minimum point, will be the middle of pi and 2 pi, in other words 3 pi over 2. And the maximum minimum values will be 1 and -1. So how do I know these numbers? I know these numbers because we actually know that sine and cosine are always nested between -1 and +1. And of course, your cosine, we expect it to look like this. Down, down, up, up. Once again, we'll have 1 and -1. The middle will still be pi. The end point will still be 2 pi. And these two cutting portions will be multiples of 90 degrees. In other words, 3 pi over 2 and pi over 2. Right? So these are pretty straightforward graphs. If you need to look at them, pause the video for a moment. Otherwise, let's move on and talk about the general case scenario. What if we have a coefficient on the trigo? What if we have a coefficient on the algebra inside the trigo? And what if we have a constant term that is added or subtracted external to the trigo itself? So in this particular situation, we will have to follow the rules over here. Now, in general, the y-intercept for sine, because you used to start from 0, you used to start from nothing, what happens is that when you plus a constant, you'll start from the constant instead. For cosine, it's a little bit different, unfortunately. And the range of values will now be different because the amplitude changes, right? This is perhaps the most important thing over here. The amplitude will actually be the coefficient of the trigo. We're assuming, of course, that the coefficient is positive. If the coefficient is negative, when you write down the amplitude, make sure you remove the minus sign, right? Because if you remember, we defined amplitude in math as the distance from the axis to the maximum or minimum. Distance would mean you can't have a minus sign, right? It doesn't make sense to say -1 meters of distance. Sure, if it's displacement, then yeah, you can talk about that, but we are in a math class, so don't worry too much about it. Now, aside from that, there is also the matter of the period. This one is what people tend to forget, which is that the period will actually be 360 divided by b. This 360 here is essentially the original value of the period, and then we'll divide it by the coefficient of the algebra. So that's what we need to know, and we have a few examples over here, right? You can look at the changes in the amplitude and in the axis, which is marked out for you in dotted lines over here. You can also see how the maximum and minimum values, as well as the y-intercept, might or might not change. Right, so let's look at some examples, right? Why don't we just get our hands dirty? It's a little more, I think it would prove my point a lot quicker. And we're gonna do this in radians as well, just to challenge ourselves a little bit. So the first example here is y equals to cosine x. We literally saw this, what, 5 minutes ago? So you'll have this shape. Right, pretty straightforward. For the second one, however, this is a little more interesting. This time around we have 4 cosine x. In other words, our amplitude is 4, our period is still 360 degrees. So what happens is, you need to imagine your cosine graph, but now it is taller. And because your amplitude is 4, not only will you reach a maximum of 4, but you'll also reach a minimum of -4. Fortunately for us, in this specific situation, the remaining labels are identical. Alright? The next one is even more interesting. We have 4 cosine x minus 3. Oh boy. So now we have an amplitude of 4. Period still the same, 360 degrees, alternatively 2 pi. And this time around, we need to change the axis. It is now at -3. So I want you to imagine, right? Let's draw in the axis first. This is a pro tip. It'll make your life easier. We draw in the axis first, which is the horizontal line y equals to -3. Then we will draw in our cosine graph, which will be down, down, up, up. Right? Down, down, up, up. Then I'll draw in the y-axis without labeling anything yet. And because the amplitude is 4, what would that mean? It would mean that I have to travel 4 steps up and 4 steps down to reach the maximum and minimum values. Since we're starting from -3, we can therefore expect to have a maximum at 1 and a minimum at -7. Now that we know this, then you can draw in the x-axis, which is why I say it's better to start from the axis. You just draw in the graph first, fill in the x-axis after the fact. We expect the x-axis to be somewhere here. And of course, this minimum point is at pi. And this, oh, my mistake. Let me erase this. And then of course, this little maximum point here will be at 2 pi. Right? Of course, if you want to label these points, you can as well, but it's not that important. We would have pi over 2 comma -3, and we would have 3 pi over 2 comma -3. Now, this fourth example here is similar. We have an amplitude of 4. This time round, the period will be 360 divided by the coefficient of x, giving you 120. So you actually expect a lot of cycles here. The axis, fortunately, is at 0, and so we can go on to draw our graph. So this time round, one full cycle, down, down, up, up, one full cycle is actually going to be 120 degrees, alternatively 2 pi over 3. So we will have to go on to do our second loop, giving us 4 pi over 3, and last but not least, our final loop, giving us 2 pi as desired. The amplitude is 4, so we expect maximum and minimum of 4 and -4 respectively, and I think it's quite clear that the minimum points will always be in between values. So for example, this will be pi over 3. Consequently, that means this guy over here will in fact be pi over 6, and that guy over there will actually be 3 pi over 6, in other words pi over 2, right? And I'm sure you can figure out the rest of it yourself. This will be pi, and then this will be 5 pi over 3, right? And once you have this, let's just add in these dotted lines to make sure everyone knows the -4 attacks all of the all of the minimums, and the +4 attacks all of the maximums, and we are done. Looks a little ugly, but you'll get used to it. In fact, if you're watching this video as revision, you might be Sec 4 by now, in which case you better be used to it, right? So at this point, I want you to pause the video on this portion for a moment and compare the 4 by yourself. Look at how the amplitude evolves, look at how the period might evolve, look at how the axis might evolve. You'll notice they're all variants of cosine x. I changed the amplitude, then I changed the axis, then I changed the period. Right? So let's look at 4 more examples over here. This time around we have the negative of cosine x. So if you remember from your basic graphing techniques, for straight line graphs, parabolas, etc., that negative over there is going to cause a vertical flip in your graph. Consequently, instead of down, down, up, up, and starting from the maximum, we'll start from the minimum and we'll do up, up, down, down. And in this way, we get a flipped cosine graph. Fortunately, all the fundamentals remain the same. like so. This next problem is even more intriguing. This time around, we have an amplitude of 3. Period is the same as always, and the axis is actually positive 2, right? In fact, you could very easily rearrange this as negative 3 cosine x plus 2. Negative 3 cosine x will basically be this guy, except with the amplitude now changed to 3, and the plus 2 causes a change in the axis. Now you might be thinking at this point, wait a minute, why is the amplitude 3? Shouldn't it be negative 3? I want you to recall our discussion from earlier. Amplitude refers to a distance insofar as our A math goes. So because it's a distance, we don't care about the minus sign. So even if it's negative 3 as the coefficient of the trigo, I will still write positive 3 as the period. Right? So that will be our circumstances. And from here, we will then be able to draw our graph accordingly, right? Oh, I made a mistake. I told you guys not to don't draw the x-axis first. Start with the axis, yeah? So you can imagine this time around our axis is positive 2. So I want you to imagine the horizontal line, y equals to 2 over here. And from here, our amplitude is 3, so you expect a maximum of 5. Oh, why is it negative? We expect a maximum of 5 and a minimum of minus 1, like this. And because the cosine coefficient is negative, that means you will be having a flipped graph, right? So it's just like our previous example. We're actually going up, up, down, down. From here, then you can draw in your x-axis accordingly and do the usual labeling. I realize the labeling is quite a pain in the ass, but if you're watching this video for revision, you've probably already drawn your fair share of graphs, or at least seen others draw your fair share of graphs. So it shouldn't be too much of a surprise, right? Okay, now our last two examples over here are also pretty interesting. Over here we have an amplitude of 1, period of 360 degrees, or alternatively 2 pi divided by half. In other words, 720 degrees. And of course the axis is at 0. The reason we divide by half is because x over 2 is quite clearly just half times x. So the coefficient of the inside algebra is half. So having said that, now we can draw this graph. We recognize that a sine graph really should be like this, right? But because the period is now 720 degrees, that will mean that half of the graph is 360 degrees. And the question wants you to do 360 degrees, right? They said do it until 2 pi. So in actuality, our graph will just look like that. And we are done. It looks disgusting, but that's how it is, right? And our last problem here, oh, this one's a real doozy. We have an amplitude of 2. We have a period of, and using the same trick, this guy being 1/3 x, we will take 360 divided by 1/3. And this should give you 1080. And because of that, that means that you'll have a very small amount of the graph available. We also have an axis to worry about. It's on -1. So having said all that, let's draw in our y-axis. Oh crap, it's tilted. It's tilted. Let's try that again. Can I do straight lines? I don't think I can actually. Maybe I can and I just forgot how. It's alright. So let's imagine our y-axis over here. And this time around our axis is on -1. So let's imagine this dotted line here is y equals to -1. Now, this time around we have an even bigger issue, because if we are doing 360 degrees, then we have a cut graph yet again. The period now is 1080, which is well and good, but you're only doing 360, which is only like that, right? You have to cut the graph into 3 equal pieces. Consequently, we expect our graph to look like the piece on the left In other words, kind of like a frowning shape. So we'll go up to a maximum point and then we'll go down a little bit and we're done. That's as far as you go. The amplitude is 2, so you're going to go up here to positive 1. And at this point, right, we know that x is going to be 2 pi. So that means that our y value should be y equals to 2 sine x over 3 minus 1. Of course, sine 2 pi over 3, you can check this in your calculator yourself, will actually give you the special angle, right? It will be the square root of 3 divided by 2. So we'll have 2 times the square root of 3 divided by 2 minus 1, and that gives us root 3 minus 1. Right, so there'll be a height over here, root 3 minus 1, and it leads to our endpoint like this. Once you have that, then you can go on to draw in your x-axis and we are done. So you have an extremely ugly graph over here. Aside from your sine and cosine graphs, there is one last thing known as the tangent graph. Now this is particularly disastrous and it looks ugly, I'll say that. Fortunately, even though it looks ugly, the actual details itself are quite straightforward. So I will leave you to look at this for a few moments. One thing that you should probably pay attention to is that the period is not 360 degrees, it's actually going to be 180 degrees. And this makes sense, because if you look at the picture that is given to you, what we see is that our, how do I explain this? Is that our repeating unit, right, is actually only going to be 180 degrees long. So how it works is that we tend to think, okay, it always has to be 360 degrees, right? It always has to be like that. But the truth is, if you were to extend this drawing, what will you get? You would actually get this result. Right, let's extend our drawing. From here, why is it still blue? Let me change to orange. Also, I might also zoom in a little bit. So if we extend this drawing for further values of x, you will realize that as you go to the left, you're going to get this shape. Dot, 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 dot. That shape. So on and so forth. And over here, you're going to get this shape. Dot, 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 dot. That shape. Dot, 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 dot. That shape. And so you realize that the repeating unit is actually this extremely cursed section over here, right? You go up to infinity, you teleport to negative infinity, and then you go up to 0. That is the repeating unit. In other words, the repeating unit, strictly speaking, isn't even connected together, right? They have the asymptote at x equals to 90 degrees, or in general, odd multiples of 90 degrees. They have this asymptote in the middle. So this is a bit of a challenge that I need you to overcome, to recognize that the repeating unit can very well be disjoint in a sense. And consequently, our period is 180 degrees. And because the period is 180 degrees, that means later on, when we have more complicated tangent graphs, calculation of the period with the formula from earlier will no longer be 360 divided by b, it will be 180 divided by b. Now, another thing I want you to take note of is that there is no nice range of values to work with, because it goes up and down to positive and negative infinity and then teleports. So you can get any answer. Unlike sine, which was limited by its amplitude, cosine, which has the same challenge, tangent doesn't care. You can get tangent x equals to negative 999. You can get tangent y equals to positive 69, 420. That's perfectly okay, right? And because of that, there is no such thing as a period as well. This makes sense because the graph literally isn't even a wave, hello? So there's no way the word amplitude even makes sense. We're supposed to work with waveforms when we talk about amplitudes, right? Not necessarily waves in the sense of water waves. Physics students will well know the existence of longitudinal waves. And of course, you can work with electromagnetic waves as well. But in any case, the point is, this really isn't a wave shape. Sure, it's a repeating pattern, but you don't have any amplitude to speak of. Right? It's also worth noting that unlike the previous graphs, which were very nice wave shapes that was symmetric, tangent isn't symmetric at all. So that is also a very tragic thing to deal with. Right? So if we're okay with this, then the more generic case is actually somewhat straightforward. These different situations will all look the same as your normal tangent graph, except now the period formula, as mentioned, is no longer 360 divided by the coefficient of the argument. It's actually, no, sorry, the coefficient of the inside algebra. Instead, it will now be 180 divided by the coefficient of the inside algebra. Right? Because 180 is our new original period. So if I have tangent 2x, for example, we expect a period of 180 divided by 2, which is 90 degrees. And because our period is 90 degrees, indeed you will see that we have 90 degrees over here. Alright? Of course, this also means that your asymptotes, which are in between, will change in value as well. This time around, we have odd integer multiples of 45 degrees. If instead I have a negative sign, it causes a vertical flipping in the graph as usual, but otherwise it's basically the same thing. In particular, note that there is no amplitude to attack, and there is no maximum and minimum to attack, which means that even if you add the minus sign, you can still become positive infinity, you can still become negative infinity, and you will still teleport from one end to the other when you draw the graph. Last but not least, if the axis changes because of an external constant, just move the graph upwards or downwards accordingly. Okay, great. So looking at this, we have a few problems here to very quickly blast through. The first one asks us for 5 cosine x over 4 for 0 to x to 3 pi. Notice they didn't say degrees, which means that we're working with radians. So in this case, the amplitude is 5, the period is 2 pi divided by 1 over 4, in other words 8 pi, and last but not least, the axis is 0. From here, you can go on to draw the graph. So one thing to take note of is that your range, as they said, your range is 0 to x to 3 pi, but your period is 8 pi. And that means you will only be drawing 3 over 8 of the entire graph. So you can imagine for yourself, this is your cosine shape. I'm going to divide it into 2 pieces, divide it into 4 pieces, divide it at the 3 over 8 mark, and you'll only be drawing the first 3 over 8. Like that. Right? So having said that, we can go on to fill in did I divide it at the wrong spot? No, I didn't. Yeah, I didn't. Okay. So having said that, let's fill in this thing. I will essentially have this result. It's very small. So in order to make it look nice, please don't draw this in the exam. I want you to scale it accordingly and make it look a little nicer. So in this case, what happens is that because our graph is going to be so stubby, right? He's very short. He doesn't stretch a wide distance. I'm going to need you to artificially stretch it when you draw it in the actual exams. So let's try that again, and this time around you can go down like that, go down halfway, and then we'll stop. That's about it. we'll just stop there. Right, so your amplitude is 5, which means we'll have 5 over here, we'll have negative 5 over there, but you don't actually get to reach negative 5, of course, right? If you continue drawing the graph, then yes, you'll eventually carry on and you'll reach this part. But unfortunately, that simply does not get a chance to actually happen over here, right? And as a result, what we will have is this extremely cursed looking shape. So in addition to what we have over here, another thing to notice, of course, is that your endpoint and the middle position, in other words the x-intercept here, will also be changing, because quite obviously we're not doing 2 pi this time now, are we? We're doing 3 pi and the period is 8 pi. So a lot of things have changed compared to the original examples that we went through earlier. Right, this is actually somewhat of a challenge to work with. So what we are going to do is that we will have no choice but to actually change up all of these funny little values that we're going to get, and let's start labeling them right now. So the easiest one to note, of course, is the endpoint over here, which will be 3 pi, not 2 pi, yeah? Follow the question. And then this little intersect over here. Now this guy is fine, right? This guy will be 2 pi. How do we know it's 2 pi? Because initially, in your usual cosine graph, you cut at pi over 2. And indeed, if you substitute in 2 pi into this question, you'll get cosine x over 4, and that will give you cosine pi over 2. And therefore, the both of them lead to 0. Right? Pretty straightforward. Alternatively, another thing you can do is to simply take advantage of the fact that we actually can get the 2 pi by looking at our cosine graph as 8 different pieces, right? So previously when I drew cosine graph, I said it was down, 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 up, up, starting from the maximum. If you draw this out, what you actually see is that your cosine graph is in multiple pieces. So you will have this result: down, down, up, up. Right? 4 pieces. So if you're dividing into 8, you'll need to further splice them up like that to get 8 pieces. And so 3 over 8 will be over here. And therefore this point where you intersect the x-axis is 1 step, 2 steps ahead out of a total of 3 steps. So 2 units versus 3 units. And if it's 2 units versus 3 units, and the 3 units here is 3 pi, then obviously the 2 units where the intersection is will be 2 pi. So I think that is pretty straightforward to figure out. Of course, we're not done yet. There is one last thing to do before we're done with this question, which is we should label the coordinates of this endpoint over here. So x will be 3 pi, and y will be equal to 5 cosine 3 pi over 4. Now, when you do cosine 3 pi over 4, what happens is you'll get negative 0.707. So we'll use the square trick in order to get the special angle, right? And since we're all familiar with that, I won't waste your time doing it manually. You'll get negative root 2 over 2. Oh, sorry, negative root 2 over 2 times 5. And therefore you'll get negative 5 root 2 over 2. Alright? And that completes question 2. By the way, I see your question in the chat. It's just that I still haven't gotten a chance to answer you at all. But to answer you very, very briefly, that plus x or minus x or whatever you're working with, good news, it's not in the A-Math syllabus for those of you who are my students, but to answer the chat anyway, what happens is that because x itself is the independent variable, we can expect our graph to end up being kind of screwed up as a result. So as a simple example, you can just ask yourself, what if my x is 999 radians, right? That will mean we get negative 999 on the constant, and that is very problematic. So you can expect that even though the curvy, wavy shape of the sine and cosine graph will still be there, right? It won't necessarily be very well behaved anymore, and therefore if you really wanted to draw a graph of, for example, let's try sine x minus x, you can imagine it, instead of being a wave that is going to be horizontal, what you can expect is actually for the wave to start dipping downwards, because as x increases, you also minus by an increasing number. And as a result, very briefly speaking, you will get a silly little graph that looks like that. Yeah, it looks like trash. You can think of it as a tilted or rotated sine graph in a sense, but that's not necessarily 100% accurate either. And if you want to study the specific change in the gradient, and in that case then of course for my Sec 4 students who are watching this, it will be easy enough to work the gradient out by doing a bit of calculus. We will get cosine x minus 1, and indeed you see that the gradient itself, right, is going to be bounded by -2 and 0, which of course would imply that my gradient is never increasing, and consequently that's exactly why you see that tilted wave shape that is constantly going downwards, because the dy dx itself never can become positive, right? So all the math agrees with each other at the end of the day, as it should. So next problem, question 3 tells us y equals to 2 cosine x. 2 cosine 4x. The amplitude is quite clearly going to be 2, and the period is going to be 2 pi divided by 4. In other words, pi over 2. Part 2 then says, without sketching the graph, deduce with explanation the number of x-intercepts the graph will have. So you can just imagine, in your typical cosine graph, you travel a distance of 2 pi, and you cut one time at pi over 2, the other time at 3 pi over 2. Right now, however, it is a little bit different, because we have a period of pi over 2. Right, so this, I should have made it smaller, it's alright. So this chunk here is only pi over 2. And the graph goes until pi, which means you actually need to do a second round, right? That way you'll get a larger distance of pi. And so you'll cut 1, 2, 3, 4 times. And as for how to explain this without drawing the graph, we will simply point out to the teacher that each complete cycle gives 2 x-intercepts, since the range is until pi, that's a comma, and the period is pi over 2, we have 2 complete cycles, in other words 4 x-intercepts, and we are done. Right? So just explain it to them in painstaking detail. Make them regret ever thinking that you were going to be scared by explanation questions. We're not scared. Okay, so next portion, question 4 asks, sketch the graphs of tangent x and cosine x plus 1 on the same diagram. State the number of solutions. Of course, the number of solutions is just the number of intersections between the two graphs. We know this from simultaneous equations. So all we need to do is to actually draw this thing. Now, cosine x plus 1 is interesting. The amplitude is 1, the period is 360, but the axis is positive 1. So you're going to have to imagine we have the horizontal line y equals to positive 1 over here. And then afterwards, the amplitude is 1, so you expect to go up to 2 and to 0. From here, then you can draw in your cosine shape that you should be very familiar with now. Right? From here, the next thing to draw is our tangent graph. Fortunately, this is just tangent x, the simplest kind. So it would be pretty easy. Oh, wrong color. It would be pretty easy for you to draw the tangent graph. You can just copy it from the notes, in fact. I might as well do all the labeling for the cosine graph first. Give me a moment. Right, so this is what we'll have. And for the tangent graph, we know that this 90 degrees will now be an asymptote. And in fact, so will 270 degrees. And therefore, we should get this result over here. Right, so in this case, lucky for you, we've already labeled in the 90 and 270. You don't need to label the asymptotes again separately. Although, of course, there's no harm in doing that. That's completely up to you. But anyway, now that we have this thing drawn out, then of course we can go on to actually answer what was the objective of the question in the first place, which is to find out how many solutions there will be if we made a math problem involving these two. So as you can see, we clearly only have two intersections over here and over there, and so we conclude that there will be two different solutions. Oh, whoops. So we'll just say two solutions because there's two intersections between the graphs, and we are done. Pretty straightforward. Okay, the next problem here then says sketch the graph of blah 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 and show the coordinates of all turning points for the second part even. So for the first one, let's do that instead. This one is pretty easy, right? We have a tangent graph. It's just that your coefficient is negative. So instead of starting off going upwards, you're going to go downwards, like so. Also, you need to be careful. Your period is going to be 180 degrees over 2. In other words, 90 degrees. And therefore, that means your asymptotes are going to be at 45 degrees instead. That looks like 450. Whoops. 45 degrees. There we go. Obviously not drawn to scale. Right, so the other one will be 135 degrees. You'll cut at 90 degrees. And then we'll end off here at 180 degrees. Right? So this will be your 5A, nothing special. Having said that, let's look at 5B, which is a little more exciting. 5B asks you to draw 3 sine 3x over 2 for the very unusual range of 0 to 180. So once again, let's analyze this graph. First of all, we know that the amplitude is going to be 3. We know that the period is going to be 360 degrees because it's sine, divided by the coefficient of x, which is 3 over 2. So that will actually be 240, right? And of course the range is 180 and the axis is 0. So now you can imagine if I have one sine graph being 240 and you're only going until 180, then that will be essentially only 3/4 of the sine graph. Only 3/4. Right? So with that, we can go on to draw our graph quite readily. Let's fill in our y-axis first of all. The axis is just at 0, so you can safely draw in the x-axis as well. The amplitude is 3, so you're going down to -3 and up to +3. And this time round, we're only drawing 3/4 of this graph. So first quarter, second quarter, third quarter, and then we'll stop there. So this area here is 180 degrees. This area here is 120 degrees. That region there is 60 degrees, like so. Right? And we're done. Of course, not all questions will be so nice to tell you, oh, you can optionally label the x and y intercepts. Some questions will actually require you to calculate it out all by yourself, in which case you'll have no choice but to do so with something that we'll be learning in maybe 10 minutes from now, after we go for a second break. Right, so if we're all okay with this, then that completes our graph drawing section. Now before I move on to our final section on solving for algebra problems that contain Trigo functions, I'm going to take a second break over here. So I will see you in a few minutes, and you will hopefully see me immediately if you are not watching the live stream. Hello, hello, hello. Alright, if you can hear me, then welcome back. We will now be resuming with the final portion of our stream. So over here, now we will be going on to work with algebra problems involving Trigo. Now fortunately, this is actually pretty straightforward. The steps that you see over here is pretty much all you need to know. So I actually don't have much to explain. And if you are in a situation where the argument of the Trigo function, in other words, the person who gets attacked by the Trigo, if the person who gets attacked by the Trigo contains constants, for example plus 30 degrees, then we'll need to adjust the range of values, such as in question 1 over here. Right? And you know what? Let's do question 2 as well. I'm feeling it. We have tangent 2x equals to 1 for negative pi to x to pi. So because of that, when you're working with 2x, we will actually go from negative 2 pi to 2x to 2 pi by multiplying the inequality by 2. From here, your basic angle is going to be 45 degrees, and because of that, I don't want to write it down here. Your basic angle is going to be 45 degrees, and because of that, 2x will be equal to, it can be equal to 45, or it could be equal to 225. Well, I should be doing it in radians, but let me write it in degrees for ease of understanding first. So what we know is that the basic angle is 45 degrees. In this case, alternatively, you would have pi over 4 radians, and so you could have 45 degrees, you could have the third quadrant version, 225 degrees, right, because of 180 plus 45. And you notice that because we have negative 2 pi, we're allowed to go backwards as well. So you'll need to ask yourself, what if I'm in the third quadrant but backwards? So in order for us to work that out, what we can do is we can just go backwards by 360. Right? I need you to remember that a full round, a full revolution is always 360, and that will inform our decisions accordingly. In fact, you can do the same here as well. Right? And that will give you negative 315. So we actually have 4 different possibilities here. Now that we have this, we just need to convert them all to radian mode. So for example, we'll have negative 70 over 4 pi, negative 3 over 4 pi, let's see, pi over 4, and then afterwards, let's see, this should be, wait a minute, that's not 3 pi over 4, it should be 5 pi over 4. And therefore, if you want to find x, you'll just have to divide by 2 one more time. Right? So not too difficult, and honestly, instead of wasting time listening to me talk about how to do it, it might be more fun if we just did it, right? So let's look at some, I say some, but actually it's a lot. So let's look at some problems over here and see if we can make sense of the whole thing. Right, so for the first few problems, they're all exceedingly simple, but just for coverage sake, let's go through them anyway. So looking at question 1, we are given sine x equals to 0.7. If you want to find the basic angle, remember that the basic angle is the distance between the line segment and, sorry, not distance, separation between the line segment and the positive x-axis. Because of that, the basic angle is always acute. So we'll just inverse sine 0.7, and then we will work on from there. Question is in radian mode. Make sure your calculator is in the correct mode. This will give you 0.7753, from which it's quite clear that x will be the basic angle, or it could be the second quadrant, which will be pi minus the basic angle. Why do we choose the second quadrant? Because ASTC, you can either be an A or S, the first or the second quadrant. And so we'll have 0.775, or we'll have pi minus 0.7753, which will give you 2.37. And we are done. Please remember to leave your answers to 3 significant figures because they are non-exact. Second problem gives us cosine x over 2 equals 0.6. Fortunately, this is also pretty straightforward. The implication is that our basic angle, which is inverse cosine 0.6, will just be 0.9272. Now, the problem is we have a different range now because we're working with x over 2, and so we'll only be in between 0 and pi. Right? In between 0 and pi. As a result, even though you could be in the 4th quadrant, because ASTC, you could be in the 4th quadrant, you can. But now we have no choice but to stick with the 1st quadrant because you're stuck with this maximum value of pi. And so x will simply be obtained by multiplying by 2, giving you 1.85. Once again, to 3 significant figures. Last but not least, for part C, we're given tangent 2x is equal to 0.5, implying the basic angle is the inverse tangent of 0.5. And that gives you 0.4636. So once you have this 0.4636, what we will do next is simply to go on and ask ourselves what would happen to the rules of the game, right? So this time around, we have 2x, so we'll multiply everything by 2, and our range now expands into 0 to 4 pi. And that means we have a lot of values to work with. We can have the basic angle, we can have the 3rd quadrant, right, which is 0.4636. And in addition to all of this, right, we could even be a little more daring and start to go multiple revolutions. So for example, we know the basic angle is 0.4636, something like this. But what if we went one extra round and then went back there? So in that case, one round being 360 degrees, in other words 2 pi, in that case we would have alpha plus 2 pi, like this. And of course, you could also ask yourself, what if my pi plus alpha also goes one extra round? Right? And because of that, you'll have 4 different values, and consequently, you expect to have 4 different answers as well. Make sure to divide by 2 because the person you're finding is x. And make sure once again you leave your answer to 3 significant figures, right? Okay, so now that we have this out of the way, let's look at something more interesting. Right, so let me clear all of this. We won't be doing all the questions in this screenshot. This screenshot has a few more problems than I intend to go through. But just for your information, the next thing I want to look at is 2, and then I want to look at 4, and then I want to look at 6. Alright, so let's look at question 2 next. Question 2 tells us, first of all, to solve the quadratic 5x squared equals to 8x plus 4. Assuming you are a student of mine, I would hope that this is exceedingly trivial to you. We will start by, of course, moving everything onto the left side. So once you have this standard form of your quadratics, you can go on to factorize and when you factorize, you should get this result. Right? So once you have solved this portion, the more interesting one is what do we do with the Trigo. So we have 5 cos square A equals to 8 cos A plus 4. And I think it's very obvious that it is meant to match our part 1, right? The only difference is that x has evolved into cosine A. So in other words, we actually just have 5x squared equals to 8x plus 4, where x is equal to cosine A. And so we can borrow our part 1 answer, which is 2 or negative 0.4. Problem is, we know cosine A has an amplitude of 1. In other words, it's between positive 1 and negative 1. And so x equals to 2 should be impossible. And so we will only accept negative 0.4. Like this. So once we have this out, we can go on to solve it just like we have for all our previous problems. Just be careful of the range, yeah? It's between negative and positive 180, which is a little bit uncomfortable. Right, so let me clear up a little bit of space. Now that we know we just need to solve cosine A equals to negative 0.4, I think you'll find that this is essentially going to be the same as question 1. In fact, that's why I chose 0.4, because it's like 0.4, 0.5, 0.6, 0.7. But anyway, so cosine A equals to negative 0.4. The basic angle, once again, is the separation between the line segment and the x-axis, and so you expect the basic angle to be a positive acute angle. That means we will inverse cosine positive 0.4, despite the fact that we actually have a negative. This is only for the basic angle, yeah? So, having said that, once you feed this into the calculator, you'll get 66.42 degrees, and A can therefore be the basic angle. It could alternatively be the 4th quadrant, but the 4th quadrant, which is 360 minus alpha, will be out of range, right? It'll be too big. Our maximum is 180. So what if we did the 4th quadrant and then we went 1 revolution backwards? Now that would be appropriate. And so we will end up with this. Leave your answer to 1 decimal place because it is a non-exact numerical value in degrees. At this point you might be asking, wait, how do I know if I need to go forward revolution, backward revolution, blah blah blah? And the answer to that is you won't be able to know. You simply have to check the range in the actual question and then do it accordingly, which is what makes this particularly difficult. it will take a lot of practice, which is why this is a topic where you really have to grind a lot if you want to do well. And you really do want to do well because it's always worth a lot of marks. Okay, question 4 is also an interesting one. This time round, the arguments, the people suffering from the Trigo, that is to say, are all pretty screwed up. So let's start with the first part. For A, we are given that the cosecant of 3 theta is equal to 6. Obviously, cosecant is 1 over sine, so that means that sine of 3 theta is 1 over 6. From here, we can find the basic angle by doing inverse Trigo 1 over 6, and that gives you 9.59 degrees. Only problem is the range of values is now sandwiched between 0 and 540 because we're working with 3 theta, not regular theta. Given that we have 3 theta, then you can just go on to find all the possible quadrants. In this case, it's quadrant 1 and 2. And so we will say that 3 theta can be alpha, or it can be 180 minus alpha, or it could be first quadrant with 1 extra revolution. In fact, it could even be second quadrant plus 1 revolution, like this, right? And then from here, all you need to do is to go on to make theta the subject, and then you are done. So theta can be 3.2 degrees. Again, remember, leave it to 1 decimal place, not 3SF, because it is a non-exact answer in degrees. So you can have 3.2, you can have 56.8, you can have, let's see, in case you can't tell, I'm doing all these problems on the spot, so you're gonna have to just bear with it. Right, so this is what we will have, and if you make it this far, then you'll get your nice and juicy 3 marks. Second problem is even uglier somehow. We are given that secant 2 theta plus 80 degrees is going to give us 3. Right, so in this particular situation, what we will do is secant is 1 over cosine, so let's make cosine the subject first. Afterwards, we can find the basic angle by doing inverse cosine 1 over 3, which will give you 70.52. Now the rules of the game will change quite dramatically. We're going to get we're going to get this result. And as a result, our big bracket over here, 2 theta plus 80, can take quite a few different values. You'll notice first of all that your basic angle is 70.5, but the minimum value you want is 80. So you're already screwed. You're going to have to start with the fourth quadrant, 360 minus alpha. Afterwards, we'll do first quadrant with an extra revolution. And then you need to ask yourself, wait a minute, can I do 2 revolutions? So in this case, clearly 2 revolutions will be an overshoot, because 2 revolutions is 720 degrees. And 720 degrees is definitely way too big compared to our maximum value of 440. So because of that, we will actually just stop here, and from here you will be able to go on to make theta the subject, right? So of course, I will leave the finding of theta for you to do by yourself. Just make theta the subject, minus 80 on the right hand side, and then divide by 2. So we're almost done. The next thing is 4c. I'm not even going to erase it, I'm lazy. We're given 4 cotangent pi over 3 minus 40 degrees is equal to 5. Let's start by making tangent the subject first. Please remember cotangent is 1 divided by tangent, yeah? So I'll move the 4 over to get 5 over 4. Then I'll reciprocal the whole thing to get 4 over 5, from which we can find the basic angle by doing inverse tangent on 4 over 5. This gives us 38.65 degrees. Once you have this, we need to consider a range of values again. This time round, it's pretty unusual because we actually have this very cursed result. Like so. Wait, hold up. Yeah, there we go. Right, so I will divide by 3 on the inequality. Afterwards, I will minus everybody by 40 degrees, which then gives us between negative 40 and positive 20 inclusive. Now, having said that, we will then go on to say that pi over 3 minus 40 can give us a few different values. So what we'll do is we simply need to ask ourselves, first of all, will the first quadrant even work? And the answer to that is no, actually. We are in serious trouble. The first quadrant will not work. And therefore, we need to change our thinking a bit. How about the third quadrant? The third quadrant is 180 plus alpha, which is obviously not going to work. But what if we were to do the third quadrant and then afterwards go one extra round backwards? Would that work? So you'll perform that as well, and you'll realize, oh, wait a minute, that doesn't work either. Right? So in this case, we actually are in a bit of a dilemma over here, because it seems somewhat difficult to even find our desired values. So in a, wait a minute, my stream is being weird. Okay, there we go. Doesn't matter, I didn't write anything. But in this case, you'll realize that regardless of whether it's the first quadrant, the third quadrant, the first quadrant with one extra revolution backwards, or the third quadrant with one extra revolution backwards, you're always going to be in trouble. So what we will say is that if this guy is equal to first quadrant, third quadrant, or even third quadrant and one revolution backwards, we will actually fall out of the range of acceptable values. And so there's actually nothing you can do. This question is fake news. There's no solution at all. Now this doesn't happen too often in the O levels, but strictly speaking, there's nothing stopping them from playing these kinds of mind games with you, if they really wanted to. Of course, a good student will be able to figure it out, and you are a good student, so I'm sure things will be fine. Just make sure to pay attention to what you're actually doing, yeah? Now this next one is another doozy. We've got 6 marks in total, pretty long. So we want to solve 11 sine 2x minus 7 equals to 0. And what we're going to do is, let's start by making sine 2x the subject. You'll get sine 2x equals to 711, from which we can inverse Trigo 711 to get our basic angle, which will be 39.52 degrees. Having said that, however, the range of values is now going to be up to 720 degrees, which means that our 2x can be basic angle, it can be second quadrant, it can be basic angle with one extra revolution, or it could be second quadrant with one extra revolution. Right? So you actually have quite a bit of a disaster over here, not going to lie. But it's okay. We will just have to compute all four of these. Took a break for a moment because I had to sneeze. Anyway, let's compute these four values. Right, so these are your four values. Remember to leave them to one decimal place because they are non-exact answers in degrees. One thing to also take note of course, is that you might have seen me make the mistake. I forgot to divide by 2. Right? We're finding x, so make sure you divide by 2. You're not finding 2x, you're finding x. Remember what I said in the earlier topics, right? Doing a math paper is somewhat like customer service. Give the teachers what they want. Serve up whatever we're asking for. So having said that, let's move on to the second portion. You want to draw a graph, and notice it's a hence question, right? That makes sense because you want to label all axial intercepts and the coordinates of the turning points. In other words, you need to label the x-intercepts with the numbers in 6 part 1. So let's take a brief look over here. The amplitude is 11. The period is 360 divided by 2, in other words 180, and the axis is negative 7. So with all of that said, we're going to have to imagine, okay, this is going to be negative 7. Let's draw the horizontal line at y equals to negative 7. Once you have this, then we can go on to sketch the sine graph. The coefficient is positive, so you'll just be doing your most standard shape. Your period is 180, so for a range of 360, you expect 2 complete cycles. Also, wow, that is so not to scale. You expect 2 complete cycles. So you can imagine it as something like this. Right? Obviously not to scale, but it's alright. So now that we have this, of course, let's label our max and minimum as well. We know the amplitude is 11, and so the maximum is 4, the minimum is negative 18. From which I think it should be pretty evident that you will have your x-axis somewhere around here. Right, now that we have this, let's label in the x-intercepts. They will be the four numbers that we found from earlier: 19.8, 70.2, 250.2, and last but not least, oh, I wrote it in the wrong order. I was getting distracted by hiccups. I'm not sure if you heard them, but I was trying to suppress it. Anyway, the third number will be 199.8, and the fourth number will be 250.2, like so. Of course, once you have this, you're not done yet. You should also indicate the coordinates of the turning points, either by labeling them individually or by drawing dotted lines to see where the relevant numbers line up. So all the maximum points have a y value of 4, all the minimum points have a y value of negative 18. Furthermore, we can also go on to say that because this is a sine graph from 0 to 360, quite obviously the endpoint over here, right, over here on the right, will also be 360. Consequently, that would mean that this middle portion over here is 180. This portion here is 90. And so our turning points will be at 45, 135, and afterwards, let's see, this should be 225, I think. Right, and last but not least, we have the last minimum point, which will be at 315. Right, so when all is said and done, you'll have two maximum points labeled, two minimum points labeled, the end point labeled, the starting point, which is the y-intercept, labeled. You'll have your graph by itself, obviously, and you'll have four different x-intercepts, and these numbers will be taken from the values you calculated as the roots in 6 part 1. If you manage to get all of this out, then you will successfully get your full 6 marks. In the actual exams in the O-level, you can easily expect this to be 4 marks, not 3, in fact, because it's a pretty detailed sketch. Right, so up to this point, that completes all our content for today. If you have nothing else for me, I have nothing else for you, and we will end our stream here. Right, thanks for watching, and catch us next time when we will go into some extremely terrible stuff, namely trigonometric identities. Alright, thanks for watching, ladies and gentlemen, and now I will just chill out, maybe look at the chat and look at the DMs people are sending me on Twitter, Discord, etc. Well, Discord, I already answered them. You can see my Discord badge here, in fact. Right? So yeah, see you guys. Bye bye. Go away. Stop watching. Or if you're watching this after the fact, you should move on to Trigo identities sometime soon. I think that will be very fun, inverted commas. Okay?